In this talk, we present a model updating and uncertainty quantification of a geometrically nonlinear curved panel when it is subjected to non-uniform temperature fields. The thin structures of the advanced air vehicles show complex dynamics when they are exposed to thermal stress. Thus, the model updating of these structures needs to account for the thermal effects to correctly capture the dynamics due to heating. However, there have been fewer works on a modal correlation under thermal loading, and they assumed a uniform temperature distribution for the model updating. On the other hand, our study investigates a model updating of thin panel subjected to non-uniform temperature fields where the dynamic behavior is far more complicated. A recent experimental study of Dr. Erhardt's group revealed that modal properties of a curved panel become complex under the localized heating. As you can see in this figure, the natural frequencies and mode shapes show complex and nonlinear behavior with respect to the varying temperature fields. So in this work, we demonstrate a model updating of the thermally loaded curved panel based on their experimental data. This is an overview of our model updating procedure. Based on the experimental data, we map the coordinates and the temperature fields onto the FE model of the curved panel. And then run the modal analysis at varying localized thermal fields and update the model design parameters until their resulting linear frequencies converge to the measured frequencies. So let's dive into the actual model updating procedure of this curved panel. The default FE model had the same nominal parameter values as those of Dr. Erhardt's experimental study. So the first task is to map the temperature fields onto the FE model. There are two measurements: the XYZ coordinates from DIC data and 2D temperature data from FLIR, and they are from 4 different temperature fields. So we align the measurements using ICP algorithm, which computes the optimal transformation matrix between the DIC data and the FE coordinates. So as you can see, they match pretty well, although there are small discrepancies that may be due to the differences between the nominal geometry and actual hardware in the experiment. After the alignment, 4 sets of center-heated temperature fields were mapped onto the FE node. Since we had much more measured points than the number of FE nodes, we used the nearest point algorithm for the mapping. We then chose design parameters for the model updating procedures. Among many parameters, we chose radius of curvature, Young's modulus, and we also defined skewness constant that imposes asymmetry to the curved panel. And lastly, we defined the pre-stress, which could be represented by a uniform temperature field constant. We first updated the parameters based on the first 4 natural frequencies measured at room temperature. As you can see in this table, this number, the error between the resulting frequencies and the measured frequencies are very small. And the updated mode shapes match well with the measured mode shapes. There still exists small difference in mode shapes, as you can see in mode 2 and mode 4. And these may be due to the errors in the actual measurements, or maybe the model still is missing some features. We then wanted to see how the updated model behaves at the localized temperature fields. In order to do model analysis subjected to localized temperature fields, we performed a nonlinear static analysis that can be achieved by these key equations. So the detailed explanations about each equation can be further found in the preceding paper. So the two plots show the natural frequencies with respect to the varying temperature fields. This for the nominal model and this for the updated model. The updated model shows significantly improved agreement to the measured curves. But as the localized temperatures are applied, the trends of the curve did not change much, and they were not highly matching to the measured frequencies, especially the third modes. The mode shapes of the updated model here also suggest that the model captures the general trends but not highly accurate. For example, the interaction between the second and the third mode observed in the measurement cannot be captured by the model. Thus, we tested to update the model based on the larger number of frequency data. That is, 4 natural frequencies at 4 different sets of temperature fields were used as state variables for the model updating. The result here show that the agreement is not noticeably improved. As you can see in this table, you see the difference in the initial and updated design variables. A relatively small change of design variables resulted in a noticeable change in the frequency curves here, indicating that the model properties at localized temperature fields are very sensitive to these design parameters. Due to this sensitivity of the model properties, it becomes a challenging problem to solve for the parameter values that make an exact correlation between the model and the measurements. Also, if the parameters are very sensitive to uncertainty, then it will not be a good idea to seek a better agreement with these fixed set of parameters. So instead, what we did is run a Monte-Carlo simulation with the design parameters to quantify the uncertainties in the resulting natural frequencies. 1,000 sample sets are used, and the mean values were updated parameter values at room temperature. The standard deviation of the parameters are as follows. The frequency distribution of ±1 sigma is plotted in this figure. Here, the small uncertainty in the design parameters resulted in the commensurate spread in the natural frequencies. Most of the measured frequencies were bounded by the ±1 sigma bands, suggesting that the mean model used in the simulation is as good as expected, and we do not need further model updating procedure with this set of design parameters. Meanwhile, mode 3 could not be bounded by the 1 sigma band, which indicates we may further need additional parameters to capture this behavior of mode 3. To conclude, in this work, we tested modal updating of a curved panel that is subjected to a set of localized temperature fields. The natural frequencies at room temperature could be accurately predicted, but as the localized temperature fields were applied, it became a challenging problem to achieve an exact correlation. From the Monte-Carlo simulation, we showed that modal properties are highly sensitive to the design parameters when the non-uniform temperature field evolves. The simulation suggested that the updated FE model can be a good representation of the mean panel. That is, small uncertainty could bound the frequencies at most temperatures. And significant deviations are expected in practice due to both modal uncertainty and manufacturing variability. We experienced a demanding computational cost for the modal analysis using the full FE model, which triggers a need of reduced order modeling. So a cold mode ROM introduced by Gordon and Holkamp can be applied in our future work. This was all we had, and thank you for your attention.